day of the bootcamp. And we are happy to have Nikhil, co-organizer of the program, who will talk of diagonalization. Thank you.
Thank you, Oded. So I'm going to talk about diagonalization algorithms. And this is a topic which, despite sounding like it should have been solved hundreds of years ago, is still a topic of active research. And I will first I'll define what the problem is of devising provably efficient diagonalization algorithms for general matrices. And then I'll tell you what the obstacles to finding such a good provable algorithm are, and why maybe it's challenging to do so. Then I will tell you the main tool which has been used to surmount these obstacles over the last decade, which is a random perturbation. So this will be some kind of a structural smoothed analysis kind of result in random matrix theory. And then I'll show you how, using this result, you get algorithms that actually solve this problem. Is this handwriting readable? Okay. Okay, so let me begin by defining the problem. So I'm going to define a computational problem called approximate diagonalization. So in this problem, the input is an n by n complex matrix and a number delta, which is a desired backward accuracy. So what that means is and what's the output? What's the correct output of this problem? The output is a diagonal matrix T, also n by n, and an invertible matrix V, such that the input A is close to VDV inverse in the operator norm, up to this desired backward accuracy of delta. So we're not producing a diagonalization of A, we're producing a diagonalization of a nearby matrix, where nearby is delta. So this is the notion of backward error that was introduced in many talks that we saw earlier. And the picture associated with this is the input is some A and delta. And the algorithm takes this and does something with it and produces a pair of matrices, V and D. And this V and D are supposed to be the exact diagonalization of some other matrix, A tilde, whose distance to A is at most delta. So the notion of approximation is in the input domain.
So, Nikhil,
yes.
Does that mean that it's acceptable? It's acceptable to always return something with distinct eigenvalues.
Yes, in particular. Yeah. So this in particular, maybe I should have said, a naive way to define the problem is just return A equals VDV inverse. So that, because you can't compute roots of polynomials and so on, there's no algorithm for exactly solving this problem, even in exact arithmetic. It has nothing to do with computers.
So if A is a regular nilpotent matrix, what will this return?
It will return a nearby matrix with which is diagonalizable up to delta.
But there's essentially, so a regular nilpotent matrix, zeros everywhere except the first.
Yeah, a Jordan block, right? Yeah. That's not diagonalizable.
That's right. That's
yes.
what I'm asking.
But the point is,
but you didn't say that A is diagonalizable.
No, A is anything.
Yeah,
the point,
So I'm asking whether.
It'll return a nearby matrix and its diagonalization.
A is anything. A
Yeah.
is given.
It won't try to diagonalize a non-diagonalizing.
So it's not deterministic. So you can't.
It's not deterministic, but that's not the issue. Like this is a solution concept. This is a way to define approximation, which in your example.
Let's say the operator norm of A is 0 then.
No, it's not. It's 1.
1.
The spectral radius is 0. That's a very important point, which will come up later. Yes.
It was mentioned yesterday that computing an inverse of a matrix might not be super accurate. So in practice, how is the backward error actually computed?
In practice, how is this actually computed?
Yeah, because isn't computing V inverse sometimes?
That's a good point. So you're asking how would you certify this?
Yeah.
So it's not backward stable in the definition we've been using so far, but it is stable with some stability bounds, which I will mention later.
That's where
That will appear in the theorem.
that's why I was anxious.
Any other questions?
The wrong norm.
Okay, so I should say this is different from in numerical analysis, backward stability is a property of an algorithm. I'm using this as a solution concept, as a way to define an approximate computational problem, which is kind of more of a theoretical computer science way of doing things. First you define the problem, then you study the algorithm. Okay, now we also have to define a model of computation. The model of computation, which means what is this algorithm allowed to do, is going to be floating point. With b bits of precision. So what that means is, in every arithmetic operation, what the computer does is it takes two numbers, complex numbers. Okay, let's actually real numbers, and outputs a multiplicative perturbation of the true arithmetic on these numbers. For some epsilon, which is arbitrary, but smaller than 2 to the minus b, where b is the number of bits of precision. This is an idealized model of floating point arithmetic. But it's not that far from the truth.
So it's arbitrary operation?
Oh yeah, so this circle is addition, subtraction, multiplication, division. And then in this model, how do we measure complexity? It's worst case complexity. What we want is for every a and delta, the algorithm uses at most t of n comma delta floating point operations. So that's a function only of, sorry, this is an n by n matrix, only of the size of the matrix and the desired backward accuracy. With a number of bits of precision b, which also is allowed to depend on n and delta. So the complexity is articulated by these two functions, the number of arithmetic operations and the precision in the arithmetic operations.
Do you have any name for this kind of complexity?
Excuse me?
Do you have any name for this kind of complexity? Like, it's not Turing complexity.
Well, Turing complexity would be if you multiply these numbers, roughly. You could do that. But yeah, there's a reason to split these two resources, which is the practicality of an algorithm is very sensitive to how big this number is. If you make this number n or something, you get very, very slow algorithms. Okay, so yes.
This model seems more on something real floating point. Real floating point, we might have cancellation when we subtract two very close numbers.
Cancellation?
Yeah, if we subtract 1,000,000 from 1,000,000.01 or something, right? Then the relative error of this would be very large compared to
No, the only difference between this and real floating point is overflow and underflow. That's the only difference. Yes?
Sorry, so the b bit here is the storage or the bandwidth?
B is how many bits are being used to store each number. So let me make a remark. So when I gave this talk in a numerical analysis audience, people were very upset for a time. Because in a computer, you don't have B bits of precision. But in numerical analysis, what people do is they say you fix B, and then you ask how big is delta as a function of n and B. And actually, I'm mathematically doing the same thing. I'm just fixing delta and asking how big do you need to make B.
Epsilon is upper bound by
2 to the minus b.
Order of b?
2 to the minus b. It's 2 to the minus b. So b is b is a number of bits that's allowed to depend on n and delta. And that's the accuracy of my floating point computation.
So given delta fixed, we are trying to make b small or big.
given any delta, that let's say in this model, the user gives you I want to compute this to this accuracy. The theorems I'm going to show you are going to say, oh, you need this many bits to get this result with this accuracy.
You assume that A also given in this model.
Yes, A is also given in this model. Everything is given in this model. And I should say right off the bat that given that A is given in this model, there is actually a lower bound for this, and it's bigger than a fixed number. So this is the first time I think this has not been the first time this has been, I think, proven rigorously is in the recent paper of Shah, which shows that if you want to solve this problem as stated this way, even for Hermitian matrices, you need B to be at least log 1 over delta plus half log n, plus some log n kind of terms. Okay? So in particular, B has to go with n. If you want to do this kind of asymptotic analysis of algorithms, you cannot do it with fixed precision. Okay, so what is the okay, given the setup, what is the goal? Well, the goal is to find algorithms with small t and small b. And kind of the motivating I'm not that interested in that, but I'll mention one problem about non-existence later.
This is a result of non-existence.
Oh yeah, sure, yeah.
Lower bound.
Yeah, lower bounds. Yeah, there's a good question about lower bounds. Yeah.
That's I guess.
Yes.
The question is, I think you allow randomization, probably in the
Yes.
algorithms, maybe even in the input, I don't know.
Good
so
point.
When you say complexity, you should say
That's right.
enters.
So the algorithm is allowed to be randomized.
All algorithms should be allowed to be randomized.
Well, there's an open question about that,
No,
but
there are people.
that's very important that you're allowed to use randomness. We actually don't know how to solve this problem at all without using randomness. Okay, so motivating question kind of for this field. So I mean, okay, so Demel asked in 1997 in a textbook, which is there an efficient, numerically stable algorithm for this problem. And here, efficient, I mean, there are many ways to read this statement, but efficient, one reading is it uses small number of arithmetic operations, so t of n comma delta should at least be polynomial in n, and maybe polynomial in 1 over delta or polynomial in log 1 over delta. We can ask Jim later what he actually meant by this. Maybe he meant order n cubed, which is what he's nodding. Numerically stable. So we've seen various definitions of stability. The best thing you could hope for is this lower bound, which actually corresponds to a true notion of numerical stability that's accepted in numerical analysis. So you could ask for matching this lower bound, or you could ask for something slightly weaker. You could ask order log n over delta bits, or maybe you could even relax a little bit more and ask something about order log polylog n over delta bits. But the important thing is here, you definitely don't want a number here that's like linear in n or polynomial in n.
This is the B.
This is the B, yeah, sorry. And I think you really want C equals 1, at least. Is that, Jim, yes, okay. And for that version of the question, this problem is still open. So what's the context for asking this type of question? So there's a kind of practical context. And the situation in practice is mostly very good. So we all use, MATLAB, LAPACK, etc. There's very good software that solves this problem. So software is very fast, and it almost always works. Okay. I personally have never encountered a natural situation where it doesn't work. Yes, Tim.
Well, so many years ago, I was preparing to teach my class, and I discovered by accident a 4x4 matrix in which the classical algorithm failed. It went into a stable 2-cycle. And we put a hack into LAPACK to sort of, if you think you're close to this stable 2-cycle, take a random step in a different direction and keep going.
Exactly. So software almost always works, but it, as Jim found an example, 4x4 example where it doesn't work in 1994. And periodically people found examples like this. And as of now, there's no proof that the libraries work. So the libraries are actually some algorithm plus hacks. Okay, it's really good software, but there's no guarantee that it always works. The good thing is when it doesn't work, it tells you it didn't work. So it doesn't give you a wrong answer. So that's good. And so there's a theoretical motivation to find a provable algorithm, let's say meeting this lower bound, because then that would mean your software has a proof that it always works. And it actually gives you reliability. And maybe it's simpler and you can remove some hacks. And in theory, this is just a very tantalizing question. It's a question, it's a thing we all learn about. And for me, the thing that really made me jump up is I learned from Peter Bergesser that there was no algorithm whatsoever until 2015 for this problem. In this model of computation for solving this problem, there's actually no bound on these.
Is the conjecture or you think the Shah bound is sharp, you're saying?
Well, the Shah bound is for Hermitian matrices, Shah proved that it's almost sharp, it's sharp for Hermitian. But as I will say now, the whole difficulty of this problem is non-normal matrices. I actually don't think this is true for general matrices. I think there should at least be a 2 over here, but I don't.
When you say there's no algorithm, that means even if B is infinite, or you have real precision?
No, so I mean in this model of computation.
Yeah, but in that model, if B is infinite, the error is 0. Let's say you go to 0 error.
So if you go to 0 error, there's nothing published about this, actually. There's no published result about this in 0 error, also surprisingly.
Is it obvious that you can do something? Obviously, an easy solution?
No, it's not obvious.
Okay.
So the thing that is published is if you have integer matrices, in polynomial time, you can compute an approximation of the Jordan canonical form using B equals polynomial and n. But that's a different model of computation where you have integer exact computation.
Is that story Johan and his people?
No, it's Jin Yi Sai from 1994.
But it's never going to give Jordan form. Diagonal matrix with distinct eigenvalues, you said.
Yeah, so this is a different formulation of the problem. I'm saying there's an overkill way to solve this problem, which is compute the Jordan form in a different model of computation.
Yeah.
But in this model of computation, there's actually no theorem about this in general. I should say there's a big difference between, another important distinction is normal versus non-normal. I don't know why I'm switching colors randomly like this.
It's okay. Keeps us awake.
Okay, so normal versus non-normal. So as Mark told us yesterday, a normal matrix is one with orthonormal eigenvectors. And for normal matrices, we have known that we can get T equals order n cubed plus n squared log n over delta, and B equals more or less this lower bound. So yeah, B equals lower bound since okay, I'd say 1968. The result of Wilkinson showing that there's an algorithm that for Hermitian matrices gets this convergence rate, and it's very numerically stable. It more or less meets, it's not exactly, but more or less meets the lower bound. I should say there are some details that were not actually written down until very recently, but I would say this is known.
Do you mean normal or Hermitian?
I mean Hermitian, but you can do a trick to reduce normal to Hermitian by considering the real and imaginary part. But sure, really Wilkinson's result is for Hermitian matrices. Let's just say Hermitian. Okay, but there's a reduction from normal to Hermitian. And the real difficulty is non-normal matrices. So matrices whose eigenvectors are not orthogonal. These are the types of matrices that you see in, for example, dynamical systems, or if you're a computer scientist, you're doing the non-backtracking matrix of a graph. you might see a matrix like this. That's how I encountered these matrices for the first time. I didn't know that such matrices existed till like 2015. And now I'll tell you what's difficult about those. Yes?
This algorithm that Wilkinson did this analysis, and what is the name of the algorithm?
Yeah, so this is a very famous and very good algorithm. So this is Wilkinson, 1968. It's called the shifted QR algorithm. This is the algorithm that MATLAB, LAPACK, et cetera, everything use. OK. So let me now move on to the obstacles. So why was this the state of affairs?
Actually, once the matrix gets big enough, we use divide and conquer by.
Oh, really?
That's the base case.
Oh, OK.
The matrix is small enough.
OK, so Jim has mentioned that for moderate matrices use this. For large matrices use another algorithm called spectral bisection.
No, it's a divide and conquer just from the triangle.
Oh, I see, on the triangle. OK, so you use a different divide and conquer algorithm. OK, thanks for the correction. OK, so now let me try to give you some sense of why this non-normal case is difficult. I'll just leave the statement of the problem on the board. Okay, so I'll explain this by showing you some examples. And so the obstacle is something I'm just going to call spectral instability. Or, well, OK, maybe that's just a piece of it. The obstacle is non-normality. OK, so let me show you 3 examples, which I stole from one of Mark Embry's talks. So here's a real symmetric matrix. It's got zeros on the diagonal, and it's just half on the above and below the diagonal. So that's a Hermitian matrix. The spectrum is very nice. It's cosine 2 pi k over n. So it's an n by n matrix. And they're nicely spaced, real eigenvalues. The eigenvectors are orthogonal. And this has a very nice perturbation theory, as many of you probably know. If you perturb this matrix by, if you look at one of the eigenvalues, they're all simple eigenvalues, you perturb this matrix by some E, you get that the change in the eigenvalue is bounded by the normal V. Excuse me? S, yeah, sorry. Okay. So there's a way to label the eigenvalues, so this is true. So the changing the entries changes the eigenvalues in a nice way. The spectrum is stable under changes of the entries of the matrix. So these are 2 distinct and related properties. The eigenvectors are orthogonal, the spectrum is stable.
So,
Mm-hmm.
when you talk about this matrix, are you thinking of it as a linear map or a system of linear equations?
I'm just thinking of it as a linear map is an eigenvalue problem. So, but as we saw yesterday, those are related to linear systems. But yeah, I'm thinking of it as a linear map.
Yeah, well, that's why I got confused. But the norm, you're taking singular values.
That's right. So viewing it as a linear map, that's the natural norm that measures how much it stretches vectors. The operator norm.
I thought the operator norm was the largest eigenvalue.
No, it's the largest singular value. That's a very important distinction in this talk. I thought all those things too.
That's why I was confused before.
Yeah, so that's very good questions. Singular values and eigenvalues are different things. For Hermitian matrices, they're the same, but we shouldn't laugh. I thought the same thing. And, this is an important distinction in this talk. Okay, so now let's look at a different example, which speaks to James' point. We consider the matrix T, which is also Toeplitz matrix, has 1 below the diagonal and quarter above the diagonal. And you'll see that this is similar to S by a matrix C, which is diagonal, and just has some exponentially growing numbers on it. Okay, so that means this has the same spectrum. But because of this similarity, I've really skewed the eigenvectors, and the eigenvectors become very non-orthogonal. And there's a way to quantify that. If this is the eigenvector basis I write in a matrix V, if I write the condition number of that matrix, which we've seen several times before, it's 2 to the n minus 1. So it's exponential in the dimension of the matrix. So this is non-orthogonality of the eigenvectors, non-normality. And this has a manifestation in terms of sensitivity of the eigenvalues to changes in the entries. So in this example, if you perturb the matrix, if the matrix entries, then there exist perturbations. In fact, it's true for, in some sense, generic perturbations, that the eigenvalues will move by a factor that's actually some exponential number times the norm of E. E? There exists E, sorry, yeah. Okay. And so this non-orthogonal, I mean, I won't do the proof for you now, but this having non-orthogonal eigenvectors leads to very big instability in the spectrum as a function of the matrix entries.
So now I'm confused because if E is a perturbation, isn't like CEC inverse also a perturbation?
It is, but it might have very different norm.
Oh.
So again, it's the difference between singular values and eigenvalues.
That's what's hanging me. Yeah.
That's the whole thing. If you get nothing else from this talk, that's a very good.
No, I'm
yeah.
just having trouble wrapping my head around it. Sorry.
No, you shouldn't be sorry. I really mean this as a pedagogical point. If
This
is
for some I or maybe.
yeah, there exists I. There exists E and I. So that's, yes.
So maybe this is jumping ahead, but if you did a random perturbation or something similar also?
Yeah, so you're anticipating what's going to happen, which is this bad behavior will go away when we do a random perturbation, which is what I will say later. But before I do that, let me at least say why this is bad. Right? So why is this bad? Yes?
Just one small footnote here. This is for asymptotically small e. So you can't choose e to be over 1, for example.
That's right.
There be some kind of limit beyond which the eigenvalues don't change.
That's right. That's right.
These examples really go into Reichel and Trefethen, big literature.
In this example, you can choose e to be like 1 over poly n or something, I think. It doesn't have to be that tiny. Okay, so this is bad for 2 conceptually different reasons, actually. So badness number 1. Okay, I didn't want to write badness on the board, but anyway. So one bad thing is this non-orthogonality slows down the convergence of every algorithm that I know about, even in exact arithmetic. Okay, so it has nothing to do with floating points. So non-orthogonality slows down convergence. Now, okay, why is that? Well, one example, I mean, I'll just give you the most extreme example of this. This is kind of a heuristic. This is not a theorem, what I've written here. But one instructive example is just to consider the Jordan block, which JM mentioned. So this is not a diagonalizable matrix. So you can view this as an extreme case of what happens when the eigenvectors collapse on each other. Now, if you think about many algorithms for proving convergence of some of eigenvalues or of eigenvectors or something like that, they rely on something contracting, okay, like in the power method. And the pathological behavior that happens with this matrix is that the spectrum of this matrix is just 0. And so if you could imagine trying to run the power method on this to try to compute its spectrum, like just pick a random vector and keep multiplying by j. But you will not get anything useful until you do n of these, because if you pick a random vector r, and you start looking at j to the k times r. So you just start applying powers of j. This just shifts the entries of r. And so for a long time, this quantity is just going to be order 1 for k less than, let's say, n over 2. So for a very long time, for linear in the dimension amount of time, you're not going to get any information about the spectrum by computing applying powers of this matrix to a vector.
Why n over 2 and not n minus 1?
Yeah, n minus 1, I don't know, I'm a computer scientist. Like, just, yeah, n minus 1, sure. Well, okay, no, I'll explain to you. R will have, okay, actually, there's a good reason. There's a good reason. So if you pick a random vector, this is what I was thinking, it will have about the same size coordinates. And when you start shifting it, if you go to n minus 1, actually you will get a vector with very small norm, 1 over square root n. So you want to leave a constant fraction of the entries. It's not a total, yeah. Good question. Yes, okay. This is not a proof of this statement. There's a more conceptual way to view this statement, which is it turns out that if you have highly non-orthogonal eigenvectors, it can be shown that you are close to a matrix with multiple eigenvalues. This is essentially a result of Jim from the 80s. And there's this kind of very high-level heuristic that if you have an algorithm that's trying to converge to a solution and the solution is non-unique, then this convergence is going to be slow.
So what do the eigenvectors look like of that?
Well, this is not diagonalizable. It only has one eigenvector, which is just so this is a bit of a it's kind of a limit of examples. It's not I've just presented it because it's very dramatic. It's not actually a diagonalizable matrix. Yeah. So this condition number is infinity for this matrix. Yeah. Okay. Okay, so this is one bad thing that happens in exact arithmetic, that the convergence of algorithms, or at least all algorithms that we know, is slow in the presence of these eigenvectors. And the other bad thing appears when you start doing floating point arithmetic. So when you have this kind of instability, right? Let's say I start in floating point, I have to apply multiplicative errors to my matrix at every step, actually. That's what the arithmetic is doing. Now, in principle, I could have a proof of a theorem like this that never looks at the spectrum of the matrices that appear in the algorithm. But most proofs that I know, the way they prove convergence is they prove something nice is happening to the eigenvalues of the intermediate matrices along this algorithm. And if all of those things are being perturbed by round-off error, then this is very bad for your proof. Because this is saying that unless you use order n bits of precision, roughly, your eigenvalues are going to be highly unstable and jumping around all over the place. And it will be difficult to prove anything. So this is difficult to prove convergence if the spectrum is unstable. This is not a theorem. This is just saying that the proof techniques that we have involve looking at what happens to the spectrum as you go along this algorithm. Most of them, not all of them. I'll get to that in a moment. And those proof techniques will not work if your floating point error is just throwing your eigenvalues all over the place. And so really the issue that non-normality presents is it's not really that, what if your input is non-normal? Because in principle, and we'll see this later, if your input is not normal, you could find a nearby problem that maybe doesn't have these problems and solve that. Because after all, the goal of this type of notion of approximation is to solve well-conditioned problems, not to solve ill-conditioned problems. But the real annoying thing is, what if these kinds of bad matrices appear somewhere in the middle of your algorithm here? So how do you prevent this from appearing anywhere in the execution of your algorithm? Yeah, so I would say the kind of overall challenge is how do you prevent this from happening during the execution of the algorithm, both from a provability perspective and from a speed of convergence perspective, this is actually a real thing that happens. That your algorithm will start converging slowly. So any questions or comments on this before I move on to how you get around this? Yes?
Maybe in naive terms. So the eigenvalues, I think we depend continuously on the matrix.
The eigenvalues.
But this is not, somehow doesn't appear to be useful. I think this is true, right?
The eigenvalues depend continuously on the
matrix. It doesn't appear to be useful in this context because, you want to have some Lifshitz continuity. It's somehow,
that's right.
It's continuous, but it's bad.
That's right. So one way to
another measure, right?
Exactly. So the eigenvalues are still continuous functions of the matrix, but the blow up in the error can be exponential on the side of the matrix.
The singular values are also continuous?
Singular values are also continuous.
But you're saying that if I take a random E and I perturb the Jordan matrix with that, does it become nice?
That's the next section of the talk, yeah.
Even if E is arbitrarily small in this form?
Well, I'll prove a very quantitative theorem telling you what happens. Yeah. Yes?
So then, just to clarify, when you said, so also should we have some sort of dependence on the condition number of your matrix? Because you're saying you want these algorithms to just be good
in this
good condition, right? Yeah.
So that's the beauty of backward error analysis. What does the statement tell you? It tells you if your problem is well conditioned, which means the answer doesn't change much if you perturb the matrix, then this just works.
Okay.
And if your problem is not well conditioned, then this doesn't really tell you anything. It just tells you solve a nearby problem, and that's okay. Yeah. So that's something I guess that's come up a few times. That's what's so nice about this definition of backward error. I was talking to Lin the other day, and he said, what this tells you is when you have a bound like this, then what it means is don't blame the algorithm. The algorithm did the best that it could.
I thought this is from Jim's textbook.
It's from Jim's textbook?
Yeah,
oh, okay. Well, I heard it from you, so yeah. Okay. I only read some parts of Jim's textbook. But, yeah. Okay.
It was Wilkinson's idea.
It was Wilkinson's idea. Okay, yeah. That's okay. So now let me tell you how you circumvent these issues. And this is going to be by adding a random perturbation. Okay. So first, let me quantify these. So there, it seems that. Sorry, there's one more. Okay, I'm going a lot slower than I wanted to. There's one more thing I want to quickly mention. Example 3. You can also have a matrix. This matrix is due to Wilkinson. Is this visible?
Yes.
Yeah. Okay. So this is a 1D Schrodinger operator with a potential that goes up, just down and up like this. It's a Hermitian matrix. And this matrix, the eigenvectors are fine. They're orthogonal. Everything's great. But the gap between the eigenvalues of this matrix is tiny. So the two extreme eigenvalues of this matrix, the gap is roughly 1 over n factorial squared for this 2n by 2n matrix. It's a symmetric matrix. Now, this doesn't have spectral instability. But let's say you have an algorithm that's trying to diagonalize a general matrix, and this appears somewhere in there. This has two eigenvalues that are extremely close. What that means is if you apply a perturbation that's exponentially small, you can collapse the eigenvectors and then perturb them kind of arbitrarily. So if you have these tiny eigenvalue gaps, it can create a situation where it's easy to create non-orthogonal eigenvectors. And so, I just mentioned this very slowly, but very quickly. But the key point is that tiny eigenvalue gaps are another kind of obstacle to analyzing these algorithms in floating point, because of this issue that you can collapse eigenvectors and then create something that's highly non-orthogonal. Okay.
This is a matrix for which the shifted QR.
This is a matrix for which shifted QR what? Would work?
You earlier said like the matrix is.
Okay, so I told you there's a little caveat that in 1968 it was proven that it works in exact arithmetic. It was not actually proven it works in finite arithmetic. And you need a little bit of random matrix theory to prove that, as far as I know. So you need to actually break these small eigenvalue gaps to make it work in finite arithmetic.
This is like an example. Well, I learned that if you have a symmetric matrix, computing the eigenvalues is not very hard, but eigenvectors is difficult. And this is why.
Yeah, this is why. So yeah, to Peter's point, mathematically, what this is saying is, if you look at, I don't know, maybe the second eigenvector, or okay, the eigenvectors stop having names when they collide, but basically if you look at an eigenvector of this matrix, it can change macroscopically for an exponentially small perturbation. This is what Peter is saying, that the eigenvalues are very well conditioned, but if you have tiny gaps, the eigenvectors can fly around a lot. Yes?
I'm reading the W matrix. Tridiagonal with ones and ones above and below the diagonal.
Yeah.
And the diagonal just counts down to 0
Yeah, and
back
counts
to
up.
1.
Yeah.
Does it skip a value going from 0 to 2?
No, it doesn't skip a value. Sorry, that's the type.
Okay. Thank you.
Schrodinger operator with a potential that looks like this. Yeah. Okay, so how do we surmount these difficulties? So the idea, which in this context is due to Brian Davies, is, well, if you want to prove this kind of result, don't try to diagonalize the matrix you're given. Try to find a perturbation which solves these problems. So so given A and delta, let's call it A naught be A plus delta over 2E for some well-chosen perturbation.
I thought we were going to choose it randomly.
Well, what he suggested was well chosen, actually, and then he did some experiments that suggested that random work. I mean, no, but there's a question about this, which I'll mention at the end. We don't know how to do this without randomness. Okay? So you want to choose a perturbation, or okay, maybe random, and then just run the algorithm on this perturbed matrix with, let's say, error delta over 2. So this is some slack that this backward error model gives you. You're allowed to perturb the input. So why don't you use half the perturbation to regularize the problem and then solve the problem on this regularized A naught. So this is a beautiful idea of Davies. And he conjectured that there exist perturbations that do this. And so the type of theorem that ultimately allows us to overcome these obstacles is a theorem saying that random perturbations actually do that. So to make that precise, I'll have to define some quantities to capture this non-orthogonality and the gap. So given A, which is diagonalizable with simple eigenvalues, I'm going to define two numbers. So I'm going to define kappa v of A to be the condition number of the eigenvectors of A. So they're not uniquely defined, so I'm going to take the minimum over all diagonalization. And I'm going to define the gap of A to be the minimum gap between two eigenvalues. And so the thought you should have is, if these numbers are exponential, there's some instability. And if these numbers turns out polynomial, that's good enough to get some results. So now there's this theorem, which I'll call theorem R for regularization. And what it says is, for any matrix, any delta, or I'll just write it this way. So given A and delta, let G be a matrix of IID complex Gaussians normalized by n. So this is the right, root n. This is the right normalization that makes this thing have norm order 1 in expectation. Then, with probability 1 minus order 1 over n, the following things are true. If you look at the condition number of the perturbed matrix, this is bounded by order n squared over delta. So it becomes a small polynomial in n. And the second thing is, if you look at the gap of this perturbed matrix, this is at least some constant times n squared over delta over n squared. Okay, so if you add a delta perturbation, both these things become like small polynomial, of course, depending on the size of the perturbation. Yes.
First of all, in the definition, the E is not part of the input because you minimize over.
You're right. V is not part of the input.
Yeah. Simple.
Just give an A with simple I.
There is a condition number for problem. I think Nikhil doesn't have it, and we also have it in our book. I mean, for eigenvalue.
So your
vector computation, is it exact? It must be related.
Yes, you're raising a very good point. So you can. So what Peter is asking is, are these are two numbers associated with matrix? One about the eigenvectors, one about the eigenvalues. What Peter is asking is, are these related to the condition number of the diagonalization problem?
Yes.
And so here's a remark, or I guess it's a proposition, but I'm not going to prove it. If you have two matrices and you consider their diagonalization, so diagonalization of A minus diagonalization of A plus E, where by diag I mean the pair V and D, where let's say V is normalized to have unit columns and normalized to have, there's a phase, but let's forget about that, okay? Then you can ask how much can this whole diagonalization change if you perturb the matrix? And the answer is, this is order, I think there's n here, actually, okay, I'm not, actually I don't think there's n here. It's just order of kappa V of A divided by gap of A. There might be an n here, okay? 4, times norm of E. For E that's smaller than 1 over this number. Okay. So what is this telling you? It's in the language of condition number that Olga introduced, it's telling you that the condition number of the diagonalization problem is just the ratio of these two quantities. Does that answer your question, Peter? Okay, so let's define diag of A. So assume A is diagonalizable. Actually, assume A has simple eigenvalues. Diag of A is just a tuple V comma D, where this is not unique. If I just say this, so let's say I don't know, V has columns of norm 1, and okay, you need some way to normalize this phase of the.
Are you saying that exists a diagonal matrix with this property because there are many possible Ds, right?
Right. So the only annoying thing here is you can multiply D on the left and right by a phase, right? That's the only annoying thing left. If you normalize the eigenvectors, eigenvectors to be unit.
Sorry, different eigenvectors.
Yeah. So okay, you need to quotient out by the phases.
Yeah, okay, it's harmless.
That's harmless. But what Peter is saying is that the stability of the whole, if diag of A is the function that produces a normalized diagonalization of a matrix, the stability of that function is given by the ratio of these two numbers. There might be a square here. Okay, somebody can correct me if they're right, but it's polynomially related. Yes.
And so the norm of the tuples is like the sum of the norms of the individual.
Let's say, yes. Okay. So I don't care about polynomial and n factors in this talk right now. So let's just, all norms are equivalent, poly n factors here.
see, when you talk about the spectrum, essentially you're going to go to characteristic polynomial. So this, actually, all these remarks are just polynomials. You have a polynomial, a fixed degree, you perturb it, and
It's a good point. So you're saying these are questions about polynomials because you can write a characteristic polynomial, you can perturb the coefficients, and that will perturb the roots. These are not questions about polynomials because if you right. So but let me say why.
The way you started here right now, you forget what happens. It's only polynomial. It's only about polynomial because you want to take the distance between perturbation of the eigenvalues. It's only zero.
Oh no, that's a very important point. So I'm measuring. So E is a perturbation to the entries of the matrix. That's very different from a perturbation to the characteristic polynomial. If you,
it's very easy to relate.
But the relationship is exponential in n. That's the problem.
Polynomials.
No, it's exponential.
Determinant of determinant.
Exponential in n.
Characteristic polynomial.
Sorry, it's not. It's the magnitude is exponential. That's what he's saying.
Like you get a prefactor of. So this is another thing I learned. So my first algorithm for diagonalizing matrices is write the characteristic polynomial, compute the roots, etc., etc. But the sensitivity of the roots to the coefficients of the polynomial has a 2 to the n, or at least n factorial factor in it. That's the problem. That's why that's not a good algorithm.
I have a story here. I wrote.
You forget about Hadamard inequality. You see, you take A plus E minus A, and you take Hadamard inequality. It's just the product of the, let's say, each norm. It's to the power n. It's not exponential. You don't take determinant like expanding.
Right. So I agree with you, but now you're talking about the matrix. Right? Yeah.
The story is I wrote with Felipe a paper on that, on condition of computing characteristic polynomial of Gaussian matrices. Then it was rejected because people said, numerical analysis journals rejected because they said it's known, but it is nowhere written. Like, so it's something,
Computing characteristic.
Everybody seems to know in the area, but it's not.
Computing characteristic polynomial.
There is confusion about it, as you can see.
Well, we should discuss it later, but the important conceptual distinction is if you ask about how much do the eigenvalues change when I perturb the entries of the matrix, that could have a different answer from how much do they change if I perturb the characteristic polynomial. Okay.
Nikhil, can I ask a quick question?
Yes.
I'm just confused about why is the gap not a relative gap? Couldn't I make the condition number really good just by scaling up the?
You could define it relatively, and then there would be a norm of A. You're right.
I'm saying as stated.
I see. Yeah, maybe there's a norm of A here. Yeah. Thank you. Yeah, you're right. It has to check out that. Yes.
Sorry, last one. I had a question about the gap. So if instead of asking for eigenvectors, you ask for invariant subspaces or something like this, could the gap go away?
Right. So you're asking a great question. Here I've asked for a version of the problem in which I want to produce a full eigenbasis. You could ask for a version in which I just want to produce some invariant subspaces of higher dimension. And then there would be a different notion of condition number, which would only depend on gaps of eigenvalues in different invariant subspaces. And that would indeed be a different problem. Okay, so I'm very far behind schedule, but I'm very happy with the questions. So I'm not actually going to tell you the proof of this theorem, but I'll tell you that there are two proofs.
Tell us on a different blackboard.
Oh yeah. Okay, so or maybe before telling you the proof. So what does this? So in light of what's written here, the ratio of these quantities is the condition number of the diagonalization problem. And what this theorem is telling you is if you add a random perturbation, that condition number becomes polynomial. So this is really a smoothed analysis, in the language of Spielman and Tang, of the condition number of the eigenvalue problem. So previously this was done for linear systems, and this theorem may be viewed as a kind of version of that for eigenvalue problems. Okay, so let's see. I have very little time. So I'm not going to be able to describe any algorithms in detail here, which is fine because somehow, actually this is maybe the main point. Okay, I can either show you a picture which you will not forget about how to interpret this theorem, or I can tell you about the proofs of these theorems. So who wants the picture? Who wants the proofs? Okay. So I should say this theorem in this form is due to Banks, Kulkarni, Mukherjee, and myself from 19. But actually, after we proved this, we realized that there's a work of Armentano, Beltran, Bergesser, Cooker, and Shub from 2015, which proves a geometric bound on this condition number, which uses geometric techniques to control this condition number, from which you can fairly easily derive this theorem. So this theorem should be attributed to both Peter and his collaborators and to us. And there are two very distinct, really different proofs of this. So our proof is via a notion called pseudospectrum. Which I'll say a little bit about now and show you the picture. And their proof is really based on geometry. It's based on Gaussian integration on manifolds and things like that. And it's really based on geometric interpretation of that condition number. And the bridge between these two proofs is essentially this kind of theorem of Jim, which says that the condition number of a problem is 1 over the distance to ill-posedness. So Peter's proof controls this distance using geometric techniques, and then with a few pages of work, you can conclude something about this. And our proof accesses this via a different technique called pseudospectrum. So let me now tell you what pseudospectrum is. So Mark defined pseudospectrum yesterday. So given a matrix and a parameter, the epsilon pseudospectrum is a set in the complex plane. It's a set of numbers for which the operator norm of the resolvent is bigger than 1 over epsilon. So it contains a spectrum because this is unbounded for the spectrum, but it's a bigger set. And it's also, this is an exercise, it's a union of spectra of all nearby matrices. So here I've written two numbers that measure non-normality in some way. The pseudospectrum gives a kind of more complete picture. It's a family of sets in the complex plane. And the meaning of this definition is kind of seen by looking at two extreme examples. If you have M a normal matrix, then the pseudospectrum is just a union of disks in the plane of radius epsilon. So small pseudospectrum, not normal matrices have the smallest possible pseudospectrum. You can see it can never be smaller than this. But for a non-normal matrix, this pseudospectrum can be much bigger. So in a way, the size of the pseudospectrum is a measure of the normality of the matrix, but it gives very detailed information about exactly how different parts of the spectrum behave and so on. And there's a relationship between the pseudospectrum and this quantity written here, the ratio of the eigenvector condition number and the gap, which I'll just call kappa of eig, the condition number of the eigenvalue problem. There's essentially an equivalence between structure of the pseudospectrum and bounds on that number. So the pseudospectrum of a matrix is contained in a union of disks of radius epsilon times the condition number of the eigenvalue problem. This is a fact. So if this is small, then the pseudospectrum is small. So for normal matrices, this is okay. This is I guess just an upper bound.
For normal matrices, then Ki would be 1.
Well, no, the gap could still be small, the way I've defined it, yeah. I mean, okay, there's actually something stronger, right? It contains disks of radius, just kappa v of m, yeah. And actually, I don't have time to go into this. If you choose epsilon appropriately, there's more or less an equivalence between bounds on kappa eig and
I don't understand. D of 0.
sorry, lambda I.
Okay, that looks better.
Okay, so this fact and these disks are well separated. This is kappa v, right? Yeah. And disks are separated by the gap, by roughly the gap of M. This is a structural statement about the pseudospectrum. These two properties together are equivalent to this proposition is equivalent to having some bounds on kappa v and cap. So let me just end by showing you a picture since I've run out of time. What this theorem tells you is if you take any matrix, which might have a terrible pseudospectrum. So here's a matrix. It's highly non-normal. It's some kind of Toeplitz matrix. These are the boundaries of pseudospectrum for different values of epsilon. This has a huge pseudospectrum. That means if you perturb this, the eigenvalues could go anywhere in this big region. What the theorem tells you is once you apply the perturbation, the pseudospectrum looks like this. So the eigenvalues did indeed fly all over the place. But now when you look at the new pseudospectrum of these new eigenvalues, it's actually very small. So the green is a boundary of the pseudospectrum for small epsilon. Yeah.
And the orange is the big epsilon.
Yeah.
Big epsilon, nothing changes.
Big epsilon, nothing changed, but for
some phase transition.
That's right. Roughly speaking, what the theorem is saying for epsilon about polynomial in delta over n, you get tiny, well-separated components. That's what the theorem is saying. This one has a multiple eigenvalue, but this is a Toeplitz matrix. You can create such pictures with simple eigenvalues. That's not.
What does it look like for the transition epsilon?
Well, it looks crazy, and we don't understand actually.
Because it's like one curve, and then all of a sudden it's a whole bunch of curves.
Right. So there are lots of things we don't understand about this. From a random matrix theory perspective, we don't know how to prove everything we see in this picture. But what we do know how to prove is when you do this random perturbation, you get this splitting of the pseudospectrum into small connected components at the spectral scale of delta over n to some power. Yes?
Sorry, so just on the left-hand side, so the green line is the border of the spectrum, and the pseudospectrum is on the inside or the outside?
The pseudospectrum is on the inside.
Okay.
Yeah. So black dots are the spectrum. Colored lines are outlines of pseudospectrum. Okay, so this is some structural phenomenon which is, well, you can call pseudospectral shattering, because that's what it looks like. And this is a very useful invariant for analysis of numerical algorithms. Yes.
How does the size of G relate to epsilon?
Sorry, in this picture, yeah. So in this theorem, in the pseudospectral shattering picture, you would take epsilon to be about delta over n to some power. In this picture, I just set delta equal to 1. Okay, so I was going to say quite a bit about algorithms, but I'm glad for the questions. But this is the device that led to lots of recent progress, and Jim's question is still open with log to the 1 n over delta. So this in there.
Maybe a couple of questions.
So in this picture, the eigenvalues look like they jump to boundaries with the original.
Yeah.
Is that typical?
Yeah, so it's a great question. In this picture, the eigenvalues jump to the boundaries of the original pseudospectrum. We don't have a proof of that. So in mathematical physics, people have proven this for like non-self-adjoint Schrodinger operators. And there are techniques for doing so, but we don't understand why it's true in general.
Jim's question is referring to You said it's still open. What is it exactly, this constant log?
Yeah, so Peter is asking, what about Jim's question? So I really should have said this. So Jim's question was actually solved by Peter and his collaborators.
Yeah, I thought, yes.
Yes.
Because we were generous, just putting up
and the first algorithm for solving this problem at all was given by Peter and his collaborators, with t being order n to the 10 over delta squared, and b being order log n over delta, very close to the least you could imagine. So this algorithm is amazing in terms of amount of precision used, and it's just kind of debatable whether we can ask Jim. But it's polynomial. It's polynomial.
What question is this? Sorry.
Approximate diagonalization, the original question. How fast can you solve the diagonalization problem? And now there are a few other answers to this. So this used some geometric version of this regularization phenomenon and introduced this idea of smooth analysis, to solve this problem. And then there are some other results by Banks et al., which can do kind of a different thing. You can get a black box reduction from matrix multiplication. So log squared n over delta matrix multiplications. But now the precision is log to the 5 n over delta. This is quite unsatisfactory. This bound does not correspond to a practical algorithm, even though the algorithm is actually an algorithm that's used.
Is the worst case the Jordan block, or is the worst case known?
No. I mean, the Jordan block is actually not a very bad case for that theorem. You can do explicit calculations and see it's pretty good. The worst case is not known, also a randomized algorithm. And so we have these two extremes. We have high arithmetic complexity with very good precision based on a geometric argument, essentially. And then we have good arithmetic complexity, only the polylog worse than matrix multiplication, but bad precision. And then there's another algorithm that does n cubed log squared n over delta, which uses log squared n over delta bits of precision, which is a variant of the shifted QR algorithm of Wilkinson. But we're not there, I think, to really answering this question in the sense that numerical analysts would want it. You want an order n cubed algorithm with log to the 1 n over delta bits of precision. And all these algorithms, the first step in the algorithm is to do that. Yes?
So just in this picture, it looks like the spectrum itself, it changes a lot. Which kind of means that, if you do this, then the algorithm will return something very different.
Absolutely. Yeah, so going back to the beginning of the talk, the goal of this type of algorithm is not to solve ill-conditioned problems. It's to solve well-conditioned problems. But what the theorem tells you is that the appropriate use of the theorem is you give me a well-conditioned problem, I apply this perturbation, it doesn't change the answer, but then it gives me this invariant that throughout the algorithm, everything is well-conditioned. And that's how you prove convergence. So it is not meant to say you should solve ill-conditioned problem by perturbing them, because then we'll change the answer. Yes?
Okay, so I understand a bit the roadmap, right? So we have an intermediate algorithm that get hiccups, but we actually want to solve the well-conditioned problem. So we have this intermediate part via random perturbations. So what would bother me in scientific computing, you're somehow stuck with double precision, single precision. You're not very generous of what you can do with your precision.
Yes.
So actually that perturbation would bother me quite a bit. So is there a path forward?
Okay, so I guess two questions. Why would the perturbation bother you in terms of precision? I see why this would bother you. This would bother anybody. But the perturbation itself would bother you?
You're solving a different problem, right?
Right, but you could make the argument that if there's round off, you're always solving a different problem.
It's still backward stable.
Okay. Yeah.
Excuse me?
It's still backward stable.
Large, right?
It's still backward stable?
Delta over 2 might be 10 to the minus 15.
Right.
Yeah. You probably want it larger.
Well, okay. So some people have done, Lin did some experiment about this at some point, and what Lin did is he ran the algorithm in quad precision and added a double precision perturbation, and it seemed fine. Remember you emailed me this at some point. But the kind of picture is there's some machine precision, and you're adding noise that's somewhat bigger than that machine precision, but still very small.
But that would bother you, right? So
That would bother you. Okay. So that raises a very good open question, which is I think a deep question. Can you de-randomize this? Can you do this without adding a random perturbation? I don't know if that would fully address your question, but it's conceivable that this well-chosen perturbation could have some other nice properties that would be more palatable to numeric
it's
language.
not the randomization, it's that you pay 10 to the minus 8, right? Where you can
I see, yeah.
Expected backward error.
Yeah.
You think you deserve that. And I think that's kind of critical applications, 10 to the minus 4 versus 10 to the minus 8.
I see.
A big difference.
I see, okay.
It's not the randomization, I'm not...
Okay. I see. So you're saying in critical applications, you want the accuracy to be very close to the precision.
One I deserve. Right?
Yes, or you deserve, yes. And that's actually an interesting question. Is that attainable or not? So I mentioned this lower bound of we'll do So I mentioned this lower bound of 1 log n plus, 1 log 1 over delta plus half log n. That's a lower bound for the Hermitian case. You're kind of asking, can you achieve that bound for the non-Hermitian case? That's what you mean by deserve, right? And it's a meaningful theoretical line of inquiry to ask, what is the lower bound on precision for non-normal matrices, and can you achieve it? So for this Hermitian case, in this recent work of Shah, they have good enough bounds that you can actually prove something like for a reasonable size matrix, you do it with 90 bits of precision. So it's conceivable. It seems hard, but it's conceivable. This isn't there at all yet.
An answer to that question might be try the classical algorithm, which will work with high probability, and if it doesn't, use this. And then with high probability, it'll run fast.
Oh, okay. That's a good point. Yeah, you could do that. You could just put an if statement.
It sounds like this is sort of what's already done, in that you've added some randomness into the...
Right, we have that hacked in the current
Yeah.
Maybe
and this is like
there should be another talk.
Oh, okay.
Thanks, Nikhil, again.